Okay, so we're going to start talking today about real numbers. And can everybody see the screen okay, or do I need to turn some lights off? Now's the time to say something if it's not so good for you. We're good? Yeah, let's try. That's not the one that's going to help. Apple TV isn't connected to the network. What I'd like to talk about today is the real number system. I'd like to start by making a diagram of the general way that you can think about our real number system. So we're going to make one large rectangle to start with, and along with this I'm going to divide this into two pieces. Now the size of each piece is not relative to the number of things that are inside the square or the rectangle region, but it is to indicate that I need more space basically to write in one area of the picture versus the other. So the first thing I want us to put on the on the right-hand side is that the right-hand side are going to be our irrational numbers. Our irrational numbers are numbers like pi, other examples of irrational numbers would be radicals, in particular numbers like square root 2, where there is no definite decimal expansion. It doesn't ever end, it doesn't ever repeat. And that's the kicker. I mean, that's the deal about irrational numbers, is irrational numbers do not terminate. That means they do not end in their decimal expansion, and they do not repeat with any pattern. Another one that you may have seen, depending on what levels of mathematics that you've had before, would be the number e. Now, this is irrational numbers on the right-hand side of our chart, and the left-hand side of our chart is actually our rational numbers. And our rational numbers, and again, this is the reason I left such a large box over here, is that our rational numbers can be broken apart further, whereas our irrational numbers can't. So inside of our rational numbers, one item that we have, one type of number, is an integer. And inside of integers, another way of distinguishing or describing numbers is what we call whole numbers. And the last one that we're going to go inside here is natural or counting numbers. So that's our final small box inside, and that's actually the box we're going to start in as we're describing. These are my natural numbers. Now the natural or counting numbers are the numbers that you start counting with when you first learn to count. So when we first start learning to count, of course, we start with 1, and then 2, and then we have 3. And we keep going up. And very quickly, somewhere along the way, somebody asks us, well, I had 3 cookies and I gave the 3 cookies away to all of my friends. How many cookies do I have left? And of course the answer is 0. And when you say 0, the question is, well, that's not one of these numbers I just wrote down, so that's something else. So our whole numbers in this one start with the number 0, and then they include all the same natural numbers that we had before. And then again, it happens that somebody asks you or says to you, what happens if I have 7 and I subtract 9? And the problem, of course, is that that doesn't work. So integers, which is this arrow, I kind of wrote them in a little bit odd placement, but the integers are going to give you the negative whole numbers as well. So you have -3 and -2 and you can keep going. So you have -1. Now integers also include all the same numbers we listed before, so 0, 1, and 2, and so forth. And then along about 5th grade or 4th grade, somewhere in there, you talk about this idea of having, instead of 6 cookies and you divide them evenly among 3 people, you've only got 5 cookies and you divide them among 3 people, and all of a sudden you have to sort of cut a cookie in half to make it evenly distributed. And we run into things called the rational numbers that are not integers, so things that actually appear to be ratios. And so some of them appear to be, like my example, 5/3. They can also appear as decimal expansions, so like -1.4. Negatives are okay as well here. We have -1.4. We can write the -1.4 as a fraction, and in reduced form it will have an integer on top and an integer on bottom. Another example of what we have is that we have our numbers that would look like a repeating decimal, for instance, 0.6 repeating, which if we were to change it into a fractional expansion, it would look like 2/3 instead of 0.6 repeating. Again, it would be a ratio 2/3 of integers. Now these are our numbering systems, and what I want to show you is the notation that can be used for each of these systems for shorthand, basically symbols. The natural numbers can look like this. It looks like an N with 2 lines on the left. Our whole numbers look like a W with 2 lines on the left. Integers actually, contrary to what you might think, are not an I. They're a Z with a double line in the middle. Rational numbers look like a Q with a line on the left. Our real numbers are R. And then the irrational numbers have one of two sort of possibilities. Some books will do a double letter, so it looks kind of like the Roman numeral 2, but it's an I. That's not common notation. So instead, what you often see instead is you see the real numbers, which was that R, minus the rational numbers. So if you have the real numbers and you remove the rational numbers, clearly what is left over are the irrational numbers. Now, cardinal number, or cardinality, is actually notated N of A for a set A. And what this is this is the number of elements in set A. So we're going to do a couple of examples of this. If you take a look at problem number 4, and we're asked to find N of A, that is the number of elements in set A, we can actually sit here and we can count them. We count 1, 2, 3, 4, 5, 6, 7. There are 7 elements in set A. Now, this set A on number 5 is a little different because it's not really a full listing method. They're not all listed out. In other words, you have to, in your mind, think about what the dot's representing. So if you notice the pattern, of course, they're counting by 5s, and if we count them and we number them off with our hands as we count, we have 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And if we've counted them properly, we also will end up together with the number 10. So there are 10 elements in this set. Now, there's 2 ways of describing or classifying cardinality. One cardinality is that it is finite. So finite means there is a natural number. Actually, we need whole number, not natural. There's a whole number representing the number of elements in the set. Now, you might look at this and say, well, why did she change whole number natural number into whole number there? Why did that matter? We actually need the whole numbers for this because there is a set that has nothing in it, namely 0 elements. That's the null set. We talked about that last class period. And so we actually need the whole number 0 in order to describe the size or the number of elements in that set. Infinite is another one. So infinite means that there is no whole number representing the number of elements in the set. Now, if you think about that, infinity, we know that concept of infinity, and it means something goes on forever. So if we were to take, for instance, that last set that looked like it was 5, 10, 15, and so forth. And instead of it actually stopping at 50, we just let the dot, dot, dot indicate that it continues beyond that. This would be an infinite set because there is no 50 upon which we end our counting. So what we need to do on this next set is that we are looking for whether or not these sets are finite or infinite. So if you take a look at number 6, you can see that we have a situation very similar to problem number 5 above. We have 6, 12, 18, there's a dot, 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 and it ends at 42. Now this doesn't ask us to actually find the cardinality, but it does ask us to know whether the cardinality is counting, like I can count it. And I can, in fact, this is finite. I could count the numbers that it's describing, and it would end at 42. Now on number 7, it says x is a natural number greater than 50. This one is infinite, and the reason it's infinite is because of, in particular anyway, because of this word greater. If this had said less than 50, then this would actually be finite, because natural numbers start at 1, and then they would end here in this case at 49 if this says less than 50. However, it says greater than 50, so it doesn't, in fact, end at 50. It begins at 51, and it would continue on up from there. There's a couple of symbols that I have mentioned once before already. There are symbols that look like kind of it's called an epsilon. It looks like a curvy E. And this curvy E shape is read as is an element of. And if we want to put a line through it, this would mean is not an element of. And if we're taking a look on our next slide, we're going to see an example and a non-example of how this would work. So on problem number 8, we've got the number 7, we've got a fill in the blank kind of a spot, and then we have a list of numbers that are elements inside of a set. So we actually have a set on the right-hand side of elements. And we notice that the number 7 is in fact included in that set, so 7 is an element of the symbols, or of the set that is on the right-hand side. Now, it almost looks like number 9 has that same property. But if you'll notice, the difference between number 8 and number 9 is that on number 9, we actually have the 3 on the left-hand side inside of curly braces. What that means is that we're talking about a set. This is a set on the left-hand side now of the number 3. And there is not inside of the right-hand set a set of the number 3. We have the element 3, but we don't have the set with 3 in it. So it may feel like it's a little bit of a nuance here, and maybe we're being technical when it doesn't really seem intuitive, but we're going to see what we should put in between there later. But for now, it simply is not an element of it. It has another property. Now, set equality, an item when we have two sets that are equal, it follows this definition. So a set A is equal to set B if, number 1, all elements of A are in B, and number 2, all elements of B are in A. And if you take a look at this, there's lots of ways of writing that down. We could in fact, even for an example of sets that are equal, we could consider the set that has the numbers 0 and 1 in it. And we could talk about the set that has the numbers 1 and 0 in it. Now, these are clearly the same set. They have the same elements in them, but they're in a different order. But we would say this set is equal because each element is an element of the other set as well. Now, our last two examples are to decide if statements are true or false. So notice number 10. Number 10 says 6 is an element of the set -2, 5, 8, and 9. And this is actually a false statement because 6 is not an element of that set. It is not included in the list of elements that are in that set. Now, on number 11, we've got x such that x is a natural number less than 3. Well, natural numbers are the numbers that are our counting numbers. They start at 1, 2, 3, and so forth. So we can start our natural numbers less than 3 at the number 1, and we would include the number 1 and the number 2. There are no other natural numbers that are less than 3. So that description on the left is in fact equal to the listing method of the right-hand side. And this would be a true statement.